Yeah, so quick recap. What is the major difference between Sn1 and Sn2? Let's start with Sn2. What happens in this reaction? What sort of mechanism is it?
Substitution reaction.
Yeah, it is for nucleophilic substitution, but okay, how is it different from Sn1? Like, what is the difference between both?
Two species and one species.
Yeah, two species, one species, matlab, like, can you elaborate a little more? Because both the reactions need two species, like substitute karne wala, and then there's like a proper reactant. So Sn1, Sn2.
Sn2 needs two species, so like one should. It basically depends on the two species, and Sn1 depends on one of them only.
What
And
depends
the
on?
other one,
Determining
so they
step.
speed.
Rate of reaction. Rate of reaction.
Yeah, the rate determining step involves two species in this, involves one species in this, but that's more of a characteristic. So if you were to, if someone asks you what is the difference between Sn1, Sn2, so Sn2, the mechanism takes place in one step. But in the case of Sn1, it takes place in two steps. Okay, so that's where that whole rate determining step and other differences are coming into picture. Sn2 mein there's one step where the nucleophile is, everything is happening simultaneously. Like you have the substrate here, the nucleophile as it is forming a bond, the other bond, like with the leaving group, it breaks apart. So this is like the transition one. In the case of Sn1, so iska characteristic, why is it two steps, is step one, a carbocation is formed, and then step two, like carbocation is formed after the leaving group leaves. And step two, the nucleophile is attracted to the carbocation, forming your final product. Okay. So this is like the major important differences between Sn1, Sn2. And apart from that, like the rest of it follows. So if it comes to Sn1, Sn2, this is what you need to remember. Sn1 kya hota hai? Like formation of carbocation and then final product. Sn2 mein kya ho raha hai? Both of them, like there's a very unstable intermediate formed and the substitution happens in like a single step. The kicking out and coming in both. Okay. So I'll discuss like the differences between Sn1 and Sn2. We'll put it as a tabular form. So there are some other points that we'll cover. And after that, I'll go over a little more about the stereochemistry. Okay. Apart from, yeah, Kaveri?
I still didn't understand, what do you mean two species involved, one species involved?
So Sn2 mein kya ho raha hai? Like suppose I have OH minus plus CH3Cl. So this is Sn2. So in a single step, when this starts attacking the carbon, this also starts leaving, right? So this is the intermediate that's formed. So OH starts forming a bond with carbon. It's already bonded to the hydrogens here, while this bond starts to break. So this again, I'm putting it in dotted lines because both of these are not complete bonds. As this is breaking, this is starting to form. And this is extremely unstable because you can see that carbon is having to hold 5 whole bonds, but carbon ka valency is only 4. So this is extremely unstable and it's got extremely, like, this is a high energy state, which is why iske baad immediately it breaks down into like the substitution will happen. You have CH3, this forms completely, and Cl minus leaves. So in this single step reaction, how many reactants are involved? So that's what it means. Two species involved in the rate determining step. But in the case of Sn1, see, the first step, carbocation is formed, right? So yahan pe the nucleophile is not coming into the picture at all. It is simply, suppose I have tertiary carbon.
Second step is the attack of the nucleophile on the carbocation, right? So that involves two species.
Yeah, but that is not the rate determining step. So that as soon as the carbocation is formed, negative attracts to positive, like wo to hona hi hai. So the rate determining step, like the speed of the reaction, depends on how easily this carbocation is formed. So that's why we call it the rate determining step. And
so in SN2, the rate determining step involves two species, and in SN1, the rate determining step involves just one.
yes, that's where the 2 and 1 comes from. Okay.
Ma'am, is it possible, like you after class or right after this, could you do the table on the 300 page on like NCRT,
What
the
is that?
one with nucleophiles and all, the table? Could you go over it again?
That's just a list of nucleophiles. Okay, so after the class, I'll sit with you and figure what we need to go over in that. Okay. It's just a list, like it's like saying periodic table में ये सारे elements है. That's a list of nucleophiles that you have. अगर OH है तो final product क्या होगा? अगर iodine I minus है तो final product क्या होगा? That's what that table says. Okay, so now differences between SN1 and SN2. Let's put SN2 over here, SN1 over here. Apart from basic differences, the finer details that we discussed, inversion, like or like optical stereochemistry में differences क्या होगा, and what sort of thing will help speed up this particular mechanism, like all of those other details we'll talk about it. So SN2 में, the first point is, so the strength of the nucleophile is important. But in SN1, the strength of the nucleophile is not as important. Okay. Anyone wants to figure why this is the case? Any guesses? What do you think?
Since SN2, for example, we are taking OH or chlorine, the chlorine bonds breaks as OH is entering. But in SN1, the bond already breaks, so that is why it is not that important.
Absolutely. That's where the difference is. So if the nucleophile is not strong enough, it won't be strong enough to kick this out. Remember, SN2 mein, both of this is happening simultaneously. Think of it as going to be a tug of war between the entering nucleophile and the leaving group that's already there. So whichever is a stronger one, that's going to win in the end, which is why nucleophile strength is important. If you have a good leaving group, something where the bond will break easily, this mechanism, like it'll help for this mechanism for the final product to be formed. At the same time, you need the nucleophile that is kicking the other one out to be strong in order to form this bond. But in this case, as Rishit said, two-step hai, already carbocation form ho gaya. So whatever negative charge is there is going to get attracted to the positive charge. So in that case, it's not very significant. Okay, next. The second point, this we already discussed. Reactivity. In the substrates. So nucleophile, stronger nucleophile hai, to this reactivity will get higher. So let's look at the other molecule, the substrate that we have over here. So which will be the easiest to go through SN2? Like methyl primary, secondary, tertiary mein?
Tertiary.
Huh? SN2?
Methyl.
Oh, primary. It's
Primary. SN2 hai, like you need space over here. So methyl will be the highest, followed by primary, followed by secondary, followed by tertiary. tertiary अगर bulky है तो there is no space for the nucleophile to attack this carbon. That was the whole point. तो यहाँ पे reactivity क्या होगा?
tertiary
secondary, primary, and methyl. Me is methyl, huh? Methyl is basically CH3 in case. Okay. Next. Now the medium. So Sn2 reaction may non-polar medium will be ideal to carry out Sn2 reactions. So let's put it this way. So this reaction will be faster in less polar solvents. Non-polar would be ideal. But in this case, a good ionizing solvent would be ideal because again, Sn1 may the first step, like the possibility of Sn1 mechanism always depends on the formation of this carbocation. So we'll lose the Cl minus. So in terms of medium, like a good ionizing solvent required to stabilize the carbocation. So if you have ions, again, like dissolves like, so polar solvents are good for this thing, for Sn1 mechanism, because the mechanism follows formation of ions. यहाँ पे कोई ion formation नहीं है, and also you want to force a covalent bond to be formed. So this reaction will prefer non-polar solvents. The less the polarity, the better it is for Sn2. So this kind of helps you figure out, like suppose you have a secondary carbon, a secondary haloalkane taking part in Sn2. Then is it going to go through Sn2 mechanism or Sn1 mechanism? If everything else is matched in terms of substrate, nucleophile, everything, then look at the medium. So if it's an ionizing medium, the secondary carbocation will be stabilized by the medium. So it will go through the second Sn1 mechanism. Okay. And this ties in with the definition, the rate of the reaction. So the rate determining step rate will be equal to, again, this we haven't done chemical kinetics, but rate of a reaction ka formula aisa hi hai. So rate of a reaction R is directly proportional to the concentration of the reactants. So you introduce proportionality constant K in order to make it an equation. So rate determining step is equal to Rx. It only depends on, sorry, this is Sn2 mechanism, right? It depends both on Rx and the nucleophile. Depends on two species. But here, the rate determining step, it only depends on the haloalkane. How fast it can ionize. It only depends on this particular step. Now coming to the stereochemistry. In Sn2 mechanism, something called racemization takes place. You guys remember what is racemization, Rasomic mixture? No?
50% dextro
the
and
rotation, yeah.
So Sn2 में, again, it takes place in two steps, right? पहले carbocation form हो रहा है. Next step में the nucleophile comes and attaches itself to the carbocation. What is the hybridization in carbocations? C plus tertiary है ना, you have CH3, CH3, CH3. So ये वाले कार्बन का हाइब्रिडाइजेशन क्या होगा?
sp2.
sp2.
sp2 is correct. And sp2 का ज्योमेट्री क्या होगा?
Trigonal planar.
Trigonal planar.
हाँ, trigonal planar. Trigonal planar मतलब, like, can you visualize it? What does that look like? What does it mean?
(120°) and
Like, you can use your hands, fingers, describe it anyway.
Basically, the structure is on a paper.
Planar, it's on a single plane, flat structure hai. And as Kaveri said, 120 degrees, 3 bonds. So you can literally, like, this is what it's going to look like. You have a central atom here and the 3 bonds are over here. So let me take this, like, abhi jo screen pe dekh rahe ho, that's like vertical, right? So if I take it, put it horizontally, it's going to be flat like this, right? Iske upar hai, it's sleeping here. So when a nucleophile comes attacks, किस direction से will it attack? Sides, top, bottom, कहाँ से?
Top or bottom?
Why not sides?
I guess crowding.
Crowding, because तीनों bonds is plane पे ही है ना? Like you have 3 methyl groups here. The nucleophile can either come from the top क्योंकि ये पूरा खाली है, or it can come from the bottom because ये पूरा खाली है. So either top or bottom, 50-50%. Like 50% will attack from top, 50% will attack from bottom. So that is the reason when it comes to optical, like when it comes to stereochemistry, you will end up with 50% dextroisomers and 50% levoisomers. Like dono mirror images are equally possible. Yeah. So whenever you have a mixture of 50% dextro plus 50% levo, that is called a Rasomic mixture.
So from where will it attack?
Either top or bottom. Like the plane hai, like sp3 ka ye 3 methyl ka, if this is the plane, either it will come from, you know, behind the screen or in front of the screen. Okay, if this is the plane, if it's horizontal, either from the top or from the bottom. Okay, so this 50-50 mixture is called a Rasomic mixture. And this will show no optical activity because whatever rotation dextro is causing, the levo is going to cancel it out. So both are going to be 50-50.
Ma'am, instead of 50% dextro and 50% levo, can we say like 50% is inversion and the other is same?
Yes. So the word for that, like opposite of inversion, is retention. So 50% inversion rahega, 50% retention rahega. Yeah. That's what, like once we finish, go through all the differences, we'll talk a little more about this optical isomerism and all that. Okay, so this results in rasmization.
There is, sorry. There is inversion in Sn1 and like no inversion in Sn2, right?
Ah, yes. I forgot I put Sn2 first. Correct. I'm sorry. This is supposed to be over here. Good catch, Arya. Yeah. So there is rasmization in Sn1, like the one that forms a carbocation. So this is 50% D plus 50% L. Both are formed. All the details are the same. I was talking about Sn1, but I wrote it under Sn2. That's the only thing. Yeah. So Sn1 में what will be the optical activity? यहाँ पे because carbocation form हो रहा है, उसके बाद nucleophile attack कर रहा है, you end up with 50-50 chances. So reactant का जो भी orientation है, the stereochemistry is there. that doesn't matter at all. Like end of the day, you end up with 50-50. Now, what is the case in SN2? So if
Walden inversion.
yes, so this will result in inversion. So that inversion is called Walden inversion, like the inversion that you get results as from an SN2 mechanism. So yeah, इसमें racematization है, इसमें 100% inversion है. Again, like every molecule is inverted. So that means if I take 100% dextro mix molecule, end of the reaction, what will I get?
100% levo.
All the dextrose will become levo. But if I start off with a Rasomic mixture, like 50% dextro, 50% levo, the reaction ke baad what will I get?
But ma'am, racemization is only in SN1, right?
No, I'm not saying racemization. I'm saying if I start off with a Rasomic mixture, which is 50% D plus 50% L, and then if I make it undergo SN2 mechanism, this particular reaction, तो फिर product
It'll still be a Rasomic
50-50.
It'll still be the same. Like जो भी 50% dextro था, that will turn into 50% levo, and whatever 50% levo was there, that will turn into 50% dextro. So individual molecules will get inverted, but your final net product is still going to be a Rasomic mixture. Yeah. So at a molecular level, every single molecule will get inverted. But overall, if you need to figure out the optical activity and all, you need to see what you started off with. So in this case, it depends on your reactant, what you started off with. In this case, no matter what you take here, you will end up with a Rasomic mixture. Okay. Yeah. So another point is, in the case of SN1, there is a possibility of rearrangement. Okay. What does this mean? Rearrangement means I'm not talking about optical orientation. I'm talking about the geometry of the molecule itself. Okay. So when am I going to get rearrangement is, like, suppose I take a molecule like I have CH3, CH, then I have CH2Cl. Now, this is a primary carbon, but next to it only I have like a tertiary carbon available. So there is a possibility that, you know, this might just form a carbocation and rearrange itself to become a tertiary carbocation through hyperconjugation effects. Again, remember, everything is dictated by stability. So the molecule, whichever is the most stable way, it's going to take that. So if at all it forms a, see, if it needs to go with SN1 mechanism, there are two hydrogens, ठीक है. Lekin this is a whole bulky thing, right? Like you have carbon, which is also again attached to two methyl molecule, methyl groups. If it has to go through SN1 mechanism, then it can simply lose the Cl minus. यहाँ पे positive charge आ जाएगा. You have C, CH3, CH3H. Now, this can simply migrate here and this can rearrange itself as CH3, C plus, CH3, CH3. So your final product you might end up getting a tertiary alcohol after the nucleophile attaches itself. So this is again just one example. So that's what I mean by possible rearrangements. So in the formation of the carbocation, if there is resonance involved, or if by just migrating the positive charge, you can get a more stable carbocation, then that will happen, and there is possibility of rearrangements. In case of Sn2, there is no rearrangement because this is like direct. Nucleophile bonds itself to this, like basically wherever the leaving group is there, that's where the nucleophile attacks. So yahan pe there is no possibility of rearrangements, but because yahan pe carbocation is formed, agar form hone ke baad there is possibility of a more stable carbocation, it will rearrange itself into that other carbocation. Yeah, so this is like a case that you need to look out for when you look at mechanical reactions. Yeah.
So the example that you showed for rearrangement, I didn't understand this.
What part did you not understand? Like just go through it, look at the electron movements. Yeah.
How is the third one more stable than the second one?
What sort of a carbocation is this?
Primary.
And what sort of a carbocation is this?
Yeah, got it.
Yeah. Okay. So due to that hyperconjugation effects, yahan pe even if a hyperconjugation takes place, it will end up at tertiary because you have 3 alkyl groups, all of them electron donated. So that's what happens in the case of an allylic thing also. So that was the last point we were talking about. When it comes to allylic and benzylic haloalkanes, so they are,
Ma'am, I had a doubt. So for like 2 points, so could you explain the rate of the rate point which you did in the difference? Could you explain that point again?
so this is just expression for rate. So when it comes to rate of reaction, we have like this comes up in chemical kinetics chapter, and we haven't done that chapter. But rate of the reaction ka formula, like rate depends on concentration. If you take a lot of a substance, rate zyada hoga. So that's what it's talking about. So you derive the formula for rate of a reaction this way. So this is just putting it in mathematical terms, what we talk about Sn1 and Sn2. We say Sn2 bimolecular hai isliye because the rate depends on 2 molecules, right? The nucleophile as well as the substrate. So that's what we have put in the form of a formula here. So rate is equal to rate constant into depends on the concentration of the substrate and also the concentration of the nucleophile. But in Sn1 reactions, we say that it only depends on the substrate, like how fast this can form the carbocation. It only depends on this single step. So that's what I've put in as a formula. So rate of this reaction is equal to rate constant into the concentration of the substrate, this molecule alone.
Okay, so and also one more doubt for the inversion part, or rather for Sn1. So for resomization, so for that, so what exactly happens there? So does the nucleophile attack both the sides or something? So you told it attacks either on the bottom or on the top.
Yeah.
So if it attacks one of them, how can there be both the rightwards movements and the leftwards movement?
Again, you need to imagine that all these reactions we are not doing for singular molecules. We're taking like a mole of it, like half a mole of it. We're doing it in test tubes, which is going to consist like trillions of molecules. So when I said it can either attack from top or bottom, I'm saying that दोनों का possibility है. So, you know, nucleophile might attack like the first molecule from the top. The second nucleophile may attack the second molecule from the bottom. Like possibility is both. Yeah, ऐसे भी हो सकता है, वैसे भी हो सकता है. So if I take like 3000 molecules at a time, कुछ molecules को top से होता है, कुछ molecules को bottom से होता है. So on such a large scale where you have like trillions and trillions of molecules, you end up with 50% dextro and 50% levo.
But for example, if you observe only one molecule, then there will be either left or right, right? It won't be both.
Yeah, obviously it won't be both because there's only one nucleophile attacking on one side only.
Okay.
Yeah. Cool. Now,
Also, could you just wait for 1 minute? I was copying that.
Yeah. Right. Adat, Arnav, you guys here? Like you joined slightly late. As soon as you came in, I started.
Yes, ma'am. Yes, ma'am.
Okay, just let me know once everybody is done noting it. Just I know Sia is done. Sanskriti Arya noting Smera is done. Kaveri is finished. Arnav is done. Adat is done. Okay. Okay, nucleophilic substitution के बाद we're looking at electrophilic substitution. How many of you guys remember reactions of benzene from grade 11? Electrophilic substitution, Friedel-Crafts reactions and all that. Actually, we did it like recently also preparation mein. Chlorination of benzene. How many of you guys remember uska mechanism or at least that reaction points of that? Because we'll be repeating that again. इसलिए. Okay. So then we can like do that quickly. Finish with that. So. Okay. Adat, Rishit, you guys done?
Yes, ma'am. I pinged.
Remember. Cool.
1 minute. Done, ma'am.
Cool. Just okay, we're talking about allylic benzylic, right? Do you remember what is allylic carbon? Allylic halides.
Attached
to sp3.
Yes, any random sp3 or
Next to double bond.
sp3, yeah.
double bond, yes. Yeah. Now this is special because during nucleophilic reactions, once this bond is broken and you have positive charge here, this lends itself to resonance. You have sp2, 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 pi electrons है ना p orbital में, यहाँ पे empty p orbitals है, so this bond can keep shifting here and there. So there is resonance stabilization, which is why even though this looks primary, because of these pi electrons here, it will prefer going through Sn1 mechanism. Okay, same is the case with benzylic. Benzylic is not directly attached to benzene. It is carbon which is attached to benzene. So this particular situation is benzylic. This is a benzylic halide. Same reason here also. Like when this bond breaks and this carbocation is formed, यहाँ पे बहुत सारे electrons है, यहाँ पे empty p orbitals है, so it kind of gets included with the resonance. It is resonance stabilized. So because carbocation is resonance stabilized, it will prefer Sn1 instead of Sn2, even though it happens to be primary. So these are like special cases. Another case, in the case of the rearrangement that I just showed you guys previously. So these are like the special cases that you need to remember. Oh, allylic
Ma'am,
is another thing. Yeah. So because of this resonance, अगर ये primary रहा और ये secondary रहा, like suppose I have another CH3 here, H over here. During this resonance, because the double bond shifts here, there is a possibility that you end up with a secondary product. So you might just end up with something like this. Double bond CH2, C, CH3, H, and whatever nucleophile being attached here. So this is another example of a situation where rearrangement has taken place. Here. So
could you like tell once again for allylic how is that Sn1 like? What did you exactly tell?
So just check the recording, Rishit. I'll just say it in short. I had explained it in detail in the previous class. So resonance के लिए delocalization चाहिए, right? So delocalization specifically of pi electrons, जो p orbitals में है. So in the case of allylic, you have carbon. I'll just put like single bond sp2 सारे ऐसे है. This has empty p orbital. यहाँ पे there is like a p orbital overlap. Now these electrons, because you have empty p orbital here, again everything wants its orbitals filled. So this might pull on these electrons, like these electrons might migrate here, and you might end up with positive charge over here and the p electron shifted over here. And then again, like positive charge either hai, so these electrons will keep shifting here and there. So that's what delocalization is, and that's the resonance that takes place in an allylic carbocation. Like,
So that's why they are Sn1. That's why they're Sn1.
yeah, because carbocation is stable, right? So again, whichever is more stable, that's the route the molecule is going to take. So if it has to decide between Sn1 and Sn2, Sn1 में ज़्यादा stabilization दिख रहा है उसको, so it will undergo Sn1 mechanism.
So because the rearrangement is possible, we know that this will undergo Sn.
It's not related to the rearrangement. Resonance stabilization of the carbocation. Stability. That's what
the carbocation will rearrange to sorry
because of the resonance, because you see what's happening during resonance ki ye double bond idhar shift ho raha hai. So when the positive charge is over here, because there's like a secondary carbon possible here, so then you will observe the rearrangement. It's the other way around. It's not because rearrangement it's taking the root. Because it's resonance stabilized and positive charge is coming on to this carbon instead of being on this carbon, there's a possibility that your final product you may see a rearranged product where the nucleophile is coming attacking this carbon. I'll take an example. Suppose I have CH3, CH double bond, CH, CH2, Cl. And this I treated with aqueous KOH. So what products will be formed? Guys, this is not the time for you to switch off your video. Okay. Now, how would you decide कि कौन सा product form होगा? So in order to predict the products, you need to figure out ki, is this going to take Sn1 mechanism or Sn2 mechanism? So which mechanism will it follow? Which one?
Sn1.
Sn1 is right. But why Sn1? Because this is a primary alkyl halide.
I thought SN1 because it's an allylic halide.
Yes, there you go. Allylic hai. So if it goes through Sn1 mechanism, the carbocation can be resonance stabilized. So Sn1 mechanism is correct. So first step क्या है Sn1 mechanism का?
Formation of carbocation.
हाँ. So rest of the molecule will remain the same. But this bond breaks, it loses a Cl minus and it forms this particular carbocation. Okay, now the whole point of this following Sn1 mechanism is because there is going to be resonance stabilization in this part of the molecule. That's the whole point about allylic, this thing. Right? So what sort of resonance will you observe here? So the rearrangement you will find is a positive charge here. This is lacking in electrons. So these pi electrons are going to be shifted over here. So you'll find them being CH3, CH, CH, double bond CH2. Abhi ye double bonded electrons idhar gaye na, which means this carbon has lost electrons. The positive charge will be on this carbon. Now, if you compare both these resonance structures, if you compare this resonance structure versus this resonance structure, which carbocation will be more stable?
Second one.
Second one, right? You have a secondary carbocation as opposed to a primary carbocation. So it's going to spend more time in this form because this is more stable. So in your step 2, the nucleophile will come attack this one here. So CH3, CH, CH double bond CH2 plus OH minus is the nucleophile because I took aqueous KOH. Huh?
Miss, allylic is, you're saying that it's preferred, like it will undergo SN1.
Yes.
It can, but it can undergo SN2 as well.
It can, but this is going to be the majority product. Preferred matlab it's going to go this way.
Matlab it won't undergo SN2 only, Vesa?
No. Even if it does, it's going to be like 1%, 2%, barely, like negligible quantities. So this is going to be my major product. So if you compare the original reactant, यहाँ पे the chlorine was bonded to this carbon, but यहाँ पे the final nucleophile OH minus that you made it react with is bonded to this carbon, which means कुछ तो rearrangement has taken place. My original reactant, like it's not a direct substituent कि Cl को हटाओ OH को यहाँ पे रखो, right? So this is what I meant by possible rearrangement. And why the rearrangement happens is because of resonance, delocalization, like electrons moving around, which shifts the charges around.
It's like this is preference for allylic halide. Is there any, like, suppose there is another say benzylic, is there any
Benzylic mein you won't find rearrangement because again benzene ring is always resonance stabilized, right? So you can't disturb those double bonds which are already there. So the positive charge is resonance stabilized, but when it comes for the nucleophile to attack, it is going to be attached to the CH2 attached. It's going to be attached outside the benzene ring as opposed to being attached on the benzene ring.
Like to the chain.
Yes, to the chain.
So is that SN1?
How does that? Yeah.
How is it related to SN1 or SN2?
Sn1, Sn2 is the mechanism. That's what it relates to, right? So end product, it doesn't make a difference. It doesn't look like that. But again, coming to this point, because of the mechanisms, if you want to speed up the reaction, if you want to increase the yield, if you want to get it faster, if you know that it takes place with SN1 mechanism, you are going to use an ionizing solvent. Because if you use a non-polar solvent, that's going to reduce the rate of the reaction. It's going to defeat your purpose.
Yeah, but I didn't understand how being attached to the ring versus being attached to the chain tells us whether or not it's SN1 or not.
Yeah, so
No, that doesn't like tell us whether it's SN1 or not. Like we know that in the case of benzylic, again, benzene ring, you have a phenyl structure. So यहाँ पे already resonance is taking place. So when this carbocation is formed, so this is going to be resonance stabilized, you know, like it's the, again, this also is an sp2 carbon. So the electron cloud that is delocalized over the ring is going to extend to this pair of p electrons, pi electrons also, the way tertiary carbocations are stabilized that way.
And what about aryl and vinylic?
Very good. That's a good question. Vinylic is, again, it's a double bond. It's an sp2 carbon, right? So that's going to follow completely different mechanisms, different things at play there. But aryl carbocation, okay, aryl, this thing, which is what we are going to get to here. So yahan tak we talked all about haloalkanes, right? Whatever mechanisms we talked about and everything. Haloarenes. This is something we discussed when we were talking about phenols also. Will these undergo nucleophilic substitution? So
Electrophilic substitution.
correct. Why not nucleophilic substitution?
Because there's no electron deficient area in the.
Another way to put it is, so
Haloarenes rings in them.
can you repeat that, Adat? Haloarenes?
Haloarenes tend to have benzene rings in them.
That's why they are arenes, because they have aryl structure. But why aryl halides don't undergo nucleophilic substitution?
it's because of partial double bond.
There you go. So resonance hai, lone pair of electrons on chlorine gets involved in the resonance. Substitution ka matlab kya hai? You have to, so basically this bond breaks, Cl leaves, and another nucleophile has to get in. But in order for this bond to break, is it easy for you to break this bond, like in the case of haloalkanes, either by SN1 or SN2 mechanisms? Yes, no? Can you break this bond easily?
No.
Resonance partial double bond characteristic. This bond is slightly stronger compared to your regular haloalkanes के case में. So because you can't break this bond, nucleophilic substitution is absolutely not possible. So if you want to substitute chlorine with something else, it happens under extreme conditions. You need to give it a lot of energy in order to break this bond.
Ma'am, but wouldn't that apply for electrophilic substitution also then?
Yeah.
Again, nucleophilic versus electrophilic. What is the difference between the reagent you're using?
Nucleophilic has excess of electrons, while electrophilic is electron deficient.
That's a very fundamental difference. Besides, when you're doing electrophilic substitution, are you substituting the chlorine from the ring? No, right? Like that's a completely different kind of reaction only that's taking place. Electrophilic substitution may, one of the other hydrogens is getting replaced by the electrophile. So
Ma'am,
that-
then why is it? Oh, okay, because hydrogen.
But then
yeah.
why do we call it substitution?
Because hydrogen is.
And but in nucleophilic case, you'll be substituting like the function.
Yeah, like you'll be see, if you want a nucleophile to get in, it needs to have same properties as whatever is already there, no? So this is also a nucleophile. This is also electron rich like Cl exists as Cl minus.
But because the bond is strong, there cannot be nucleophilic substitution.
Yes, you have seen this case before. Like that's the whole reason you can't prepare haloarenes from phenol. Again, same thing. OH minus is a nucleophile. You can't simply replace OH minus with a Cl minus, Br minus, whatever the case is. Those reactions simply don't happen because this bond is, it's not very easy to break. Okay. So yeah, so that is, so there are a few more reasons. Main reason, this is the whole point of it, ki you can't like the CCl bond is difficult to break in case of haloarenes due to the resonance. Apart from that, again, nucleophilic is rich in electrons. Benzene ring, if you look at it, like if I look at it horizontally, again, all because of the resonance, I'm going to find delocalized pi electrons above and below the ring. So when the nucleophile approaches it, there's going to be repulsions. So there is heavy negative charge over here, like delocalized electrons here, which means negative charge over here. Nucleophile is also rich in electrons. So if the nucleophile approaches this molecule, it's going to get repelled very badly. Not gonna take place easily. Okay, let's say the nucleophile doesn't approach the benzene ring directly. If it has to follow Sn1 mechanism, this particular ion, like a phenyl carbocation, is very, very unstable. So this will not form, this doesn't really exist, which means that Sn1 mechanism is also completely out of the picture. Again, coming back to, if it has to form this carbocation, it means that Cl minus has to leave, which is again not possible. So yeah, so nucleic substitution is not possible in the case of arenes. Instead, haloarenes undergo electrophilic substitution. Before that, again, I mentioned that this takes place under extreme conditions, right? There is only one nucleophilic substitution reaction that chlorobenzene undergoes, which is this. So
this is just, the exception is just for chlorine or for any like nitro group or whatever. Like, no, I mean not nitro group, the ones which will be electron.
Oh, chlorine usually.
Just chlorine.
Yeah, nucleophilic substitution, no, like substituting chlorine in chlorobenzene. So when
Yeah,
you,
but like other nucleophiles can also other like chlorine, there could be other groups also attached, and on that there could be nucleophilic substitution.
this has been observed with chlorobenzene only mostly. Yeah. So again, if you just treat it like with other thing, aqueous KOH, there is not going to be any reaction at all. So you have to treat it with sodium hydroxide at 623 Kelvin. This doesn't even happen at room temperature. 300 atmospheres. This is what I mean by extreme conditions. Very high temperature, very high pressure. So this, under these conditions, so this basically, like, HCl is lost, giving sodium ethoxide, sodium phenoxide. And when you treat, again, HCl exits as H plus Cl minus, right? So within the solution, when HCl exists, shake it with a little bit of water in the presence of dilute HCl. Resolves, like this, sodium always wants to be ionic, so sodium chloride gets lost and you end up getting phenol. Okay, again, extreme case, this is the only reaction that happens, that too at an extremely high temperature and extremely high pressure. This is the only nucleophilic substitution that chlorobenzene undergoes. Rishit asked, this is a very good question. When do we know we need to use Sn1, Sn2? There is another reaction also that haloalkanes undergo, which is elimination reaction. So that also uses KOH, except that uses alcoholic KOH. So once I discuss all the reactions, we'll look at the differences between them and also give you a chart, like when do you know whether to use haloalkanes or, I mean, Sn1, Sn2 elimination kaun sa reaction hoga. So haloarenes don't undergo nucleophilic substitution, but they definitely undergo electrophilic substitution. Okay, what do you mean by electrophilic substitution? What do you remember of this? Because we have done this like a couple of times earlier, abhi tak.
Electron rich area.
Huh? Okay. Don't just give me like random words, like elaborate a little bit. Like, what do you remember of this?
Electron deficient to attack electron rich area.
Okay, that's very, very vague. We're talking about electrophilic substitution of haloarenes. So, kis tarah ke products will be formed? Tell me, like, electrophilic substitution, what all reagents have you come across? What sort of reaction have you come across? Okay, do you guys remember the production of haloarenes? Like, how do you prepare chlorobenzene in the first place? How?
Resonance.
Preparation of haloarenes is an electrophilic substitution reaction, right?
That is correct. So what reagent did you use? What reactant did you use?
Benzene is the reagent, the reactant is chlorine.
No, this is the reactant. This is the substrate you start off with. Reagent kya hai? Like, what did you treat benzene with in order to get chlorobenzene?
AlCl3.
Just AlCl3?
Anhydrous AlCl.
Anhydrous AlCl3.
Okay. बस इसके साथ आ गया क्लोरोबेंजीन.
Zn, no. Zinc, was that zinc?
You guys need to revise, man. AlCl3 से नहीं आएगा. The main reagent source of chlorine is Cl2. And then you use anhydrous AlCl3. In fact, you can use FeCl2 also. So the purpose of this is a Lewis acid. So because of AlCl3, that turns into AlCl4 minus, produces the Cl plus, which is your electrophile. So Cl2.
You can also use bromine, right?
If you want to substitute bromine here, then you use bromine. Don't just blindly learn the words, guys. Like, again, organic chemistry is all about following electrons kahan pe ja raha hai, what is turning into a positive ion, what is turning into a negative ion. Because then you can track, okay, positive is attracted to negative, or fir ye aa jayega. So the presence of AlCl3 is important because this is what, it's a Lewis acid. Do you remember what is a Lewis acid?
Electron withdrawing.
Electron
Withdrawing.
accepting. It won't withdraw electrons like from ATM. It will accept electrons from other species. Okay.
Electron accept.
Yes, electron acceptors. So they're always on the lookout of, I need extra electrons. So when you mix chlorine with AlCl3, chlorine ke paas काफी सारे electrons hai, 7 electrons in the outermost shell. So this is going to attract, this is going to go here, and then you get a complex AlCl4 minus. क्योंकि ये तो एक Cl minus ले लिया, and you'll be left with Cl plus. And now because chlorine is highly electronegative, it can't stay as Cl plus that easily. So this becomes your electrophile. And this is what it goes and attacks benzene. Okay, so all electrophilic substitutions, if you remember,
Ma'am,
how they started, Cl plus, and then if it was alkylation, Friedel-Crafts alkylation, you had CH3Cl, treating it with AlCl4, AlCl3, again, same thing, AlCl4 minus is formed, and you have CH3 plus. Okay, even nitration, sulfonation, all of them started with production of an electrophile. Yeah.
in case of chlorobenzene, like Cl, how did Cl plus, like Cl plus will get formed when it attaches itself to the benzene, right? Not before that. Cl plus will be formed when it gives its pair of electrons to the double bond that it's attached to, and then the resonance keeps on going, right?
Yeah, so then this electrophile attacks benzene. That was your next step. Benzene hai
No,
happy.
but like it becomes Cl plus after it will attack the benzene, right? Then after giving a pair of electrons, then it will get the plus charge, right?
It already gave its pair of electrons to the other Cl.
But when we draw the resonating structure, we always put Cl and then draw the arrow and then say plus because it's given the pair.
No. So benzene is neutral. Cl already has a plus charge. After it attaches itself to benzene, the positive charge migrates to the benzene ring. So then that gets into resonance. So the electrons are not moving away from chlorine. Chlorine, like the carbon that is attached to chlorine, is the one taking the double bonded electrons and like pushing the resonance in a direction.
But you said that the plus charge is getting transferred, but the chlorine gets the plus charge after it gives the pair of electrons.
It has already given the pair of electrons to the other chlorine. Like, look carefully, this pair of electrons is going here, which is why this has become AlCl4 minus. So AlCl3 took Cl minus and left behind Cl plus.
But why don't we show that in the resonating structure then?
Because benzene already has resonance taking place. where did it gets the positive charge? It's not out of nowhere. The Cl plus, Cl has taken a pair of electrons, which means one of the carbons has lost electron, which is where the plus is getting transferred to benzene.
But so like I have my last year ka notes of resonance open, and then usme you've made us write Cl and then the benzene, and then Cl is making the double bond, and then it's getting a plus charge. So already, how does Cl have a plus? Like I understood what you explained with Cl2, that how we got the electrophile. But then why don't we show the same thing when we're drawing the resonating structure? That time, we just show benzene, Cl, then Cl has we show the arrow, and then Cl is giving the bond, and then it's getting a plus charge.
That's during resonance, no? So
Yeah,
that's
so
one of
Cl plus has to attack the benzene, right? That time we just write Cl. Why?
no, it needs to be Cl plus. That means you have not noted down the plus charge there.
But ma'am, in all the resonating structures, we first show just the group, and then it's either takes or gives and gets a
Okay,
plus.
I think what you're referring to, Kaveri, look at the context. We are still in the middle of a reaction here. जहाँ पे Cl plus है, यहाँ पे अभी तक this has not lost an H plus and everything. What you are talking about is existing chlorobenzene ka. So chlorobenzene was already neutral, and when this is getting into resonance, of course, like then chlorine is giving away its electrons, isliye partial double bond is formed and everything. This is not the same as this. Think of the context, like both are not equal. This is completely different. We are talking about chlorobenzene after it has formed, when it is an independent compound on its own. Here we are still in the middle of a reaction. This was still step 1 and this was still step 2. We're talking about formation of chlorobenzene. We're talking about the middle of this electrophilic substitution reaction here.
So once the chlorobenzene is formed, then it goes into resonance, and then we show the charges.
Yeah. Either whatever charge is there, it's coming because Cl plus hai. If these electrons migrate over here, negative charge hai, it will get attracted here. Cl idhar aa jayega. Now Cl ka plus has been satisfied by this pair of electrons. But because this carbon has given away electrons, plus charge idhar aayega, and yeah, rest of the resonance will carry on. And step 3 is this is going to lose an H plus, coming back to normal neutral chlorobenzene. So in place of यहाँ पे एक hydrogen already है और Cl भी है, so this H is going to be lost as a proton, and then gives you your back here neutral compound of chlorobenzene. So when I say revise the reactions, don't just memorize the structures and the formula. Like follow the mechanism, follow हर एक electron pair को क्या हो रहा है, किस तरफ जा रहा है, and because of that, what is getting a positive charge, what is getting a negative charge, because that is what is important in organic chemistry. You're not going to get all of this as it is. You're going to get application of this. Okay. So now electrophilic substitution. First, your electrophile is formed, which then attacks the benzene ring. So that's how we got our chlorobenzene. Now we're talking about properties of chlorobenzene. So when we have an existing chlorobenzene, and suppose this is undergoing another electrophilic substitution, formation of electrophile is going to be the same no matter what reaction you see. You take the reagents. If you happen to take halogen, you get Cl plus Br plus jo bhi hai. If you happen to take, like if it's like a Friedel-Crafts reaction, then that alkyl carbocation is what is being produced. If you take nitric acid, sulfuric acid, then that particular electrophile will be produced. But whatever it is, electrophile ka characteristic will be the same. Now, what will be the product form if you already start off with a chlorobenzene? Where will this electrophile attack? Will it replace chlorine, or is it going to take some other place here?
Ortho-para position.
Correct, ortho-para position. And the reason why is it ortho-para position, not meta?
Because the plus charge would never be at the meta position in the resonating structures.
Plus charge or minus charge?
Minus charge.
Yes. Now, Kaveri, yeah, the resonating structure of the existing chlorobenzene will come into picture. It donates its lone pair of electrons. This gets into resonance. So during that resonance, you'll find that there is a negative charge ka concentration on ortho position and para position, which is what attracts the positively charged electrophile. Okay. Cool. So that's what you need to know about electrophilic substitution of chlorobenzene. Because of resonance, you get ortho and para products, no matter what electrophile it is. Huh.
Could you go back to the previous slide?
So again, the mechanism here we have done purely benzene, but the mechanism will still remain the same. Step one is always formation of the electrophile, depending on what electrophile you have. Halogenation hai to this is what it is. You have halogen, Lewis acid chahiye halogenation ke liye. You get AlCl4 minus and Cl plus, Br plus, whatever it is. The rest of it also, I'll give you a list of what are the reagents you use and what electrophile will be formed. And the second point is the difference comes in step 2. Independent benzene to pura resonance chal raha hai. But when it comes to chlorobenzene, as she said, like chlorine pe plus charge aayega, yahan pe double bond aayega, and rest of the resonance will still remain the same. We'll have negative charges on ortho and meta positions. Okay. I would suggest don't note this down because it will get confusing. Abhi we are talking about properties of chlorobenzene haloarenes. So don't note this down. This will only cause confusion again. Ki benzene kahan se aa raha hai. So directly note this down. Chlorobenzene on for electrophilic substitution, the electrophile is going to attach in the ortho and para positions.
Ma'am, could you go back 2 slides? So for this, you just was, I mean, this is not that important, right? You were just explaining something about this, right? This slide.
You need to pay attention, Rishit. Nucleophilic substitution is not possible in haloarenes.
Yeah, so that it was all about that, right? I thought there was something else you were doing it.
Yeah. So
And for the next slides, it was only about chlorobenzene's nucleophilic substitution.
Yes, this is the only reaction it undergoes. Remember these conditions because unless the temperature and pressure are this much, the reaction will not take place. And electrophilic ke liye, do not note this down. This was just a throwback to what you had already studied about electrophilic substitution. We'll talk about electrophilic substitution of chlorobenzene. Okay, so you guys have noted down this reaction?
1 minute.
So once you're done with this, note down electrophilic substitution only for haloarenes. So haloalkanes undergo nucleophilic substitution, haloarenes undergo electrophilic substitution. Sanskriti, Smera, Adit, Arnav, you guys following? Have not heard from you guys at all.
Yes.
What's the name of that ONA? You said some.
Oh, this is sodium phenoxide. So naam kaise aaya? So this is phenol, right? Like this is phenol. तो अगर H plus निकल गया तो anion आया, so it's like phenyl group plus and an O minus. So that's why we call it phenoxide. So just like how you have ethoxide from ethanol, phenoxide from phenol. Oxide ion hai because negative charge is on oxygen. Lekin phenyl group is attached to the oxygen, so it's phenoxide. Similarly, agar OH minus hai, hydrogen attached to oxygen, so it's hydroxide. Instead of hydrogen, we have a phenyl group attached, so it's phenoxide.
And this, what you've shown is like the rare case, right?
Yeah. Extreme conditions. It's not rare. If you use these conditions, ye aa jayega. And electrophilic substitution is one that I need you guys to pay attention, because this exact same reaction you will come across in every single chapter. Haloalkanes ke baad kya? Alcohols. Phenol, again, benzene ring with OH, that will undergo an electrophilic substitution. So you need to figure out ortho, para ya meta hoga. Next, aldehydes, benzaldehyde hai. That'll have electrophilic substitution. Then you need to figure out ortho, para hoga ya meta hoga. It's one thing that will repeat every single chapter. Rishit's asking, so nucleophilic substitution, haloarenes is not possible, right? Yes, Rishit. Okay, you guys done till here? Cool.
Yes, ma'am.
So electrophilic substitution, write it only for haloarenes, because haloalkanes do not undergo that. So this is the general reaction. Let's not worry about resonance abhi. And the reason why you get, so say, ortho products and para products. The reason why ortho and para, you can note down the resonance of chlorobenzene. So chlorobenzene ke resonance structures, will you guys be able to note it down, or should I do it here?
Ma'am, so in this para one is major, right?
It depends on the electrophile also, like steric hindrance and other things. Both are possible. Yes, can you draw the resonating structures? Yes or no?
Yes.
Yes, okay. Note it down. So then we'll look at the electrophiles. So agar chlorination hona chahiye, you want to introduce another chlorine group here, or in general any halogenation. So you use that halogenation, halogen X2. So it can be X, can be Cl or Br plus anhydrous AlCl3. Okay, so this will give you the electrophile, which is X plus. So this is the electrophile. So this is the reagent that we use. So अगर halogenation करना है, you want to introduce another halogen group ortho para position में, so you take a halogen with AlCl3. So the electrophile you end up getting is X plus. So Cl2 लिया तो you get Cl plus, Br2 लिया तो you get Br plus. Role of AlCl3, it's a Lewis acid. Your source of the chlorine that you would put here is your halogen. So this you need to be very clear about. Okay. Both are equally important in reaction होने के लिए. You need a Lewis acid and you need a halogen to substitute. Then, अगर nitration करना है तो okay. I'll wait till you guys are written, then we'll discuss. So nitration का meaning क्या है? What group are you introducing here?
NO2.
NO2. Yeah.
And
So in order to introduce NO2, what do you need to use?
H2SO4 and HNO3.
Correct. So HNO3 is primary क्योंकि your NO2 is coming from HNO3. And in order to produce that NO2 group, you're going to take concentrated H2SO4. So इससे you get your NO2 plus. Then sulfonation.
Ma'am, we needed to make the resonating structure of chlorine, like benzene chloride, right?
Yeah, leave some gap after the class, make it, and then after that you can scan and send. Rishit, this chapter is heavy, which is why it's taking a lot of time. Questions, we'll do it on the weekend. We haven't completed even a single topic to be able to do any question.
So what do you have to do, ma'am? Are we like we were waiting for
We'll finish
something?
off the chemical properties. Or at least if we can do till elimination reaction, उसके बाद reaction with metals is pretty straightforward. उसमें mechanism का ज़्यादा ये नहीं, it's direct. Okay, अगर ये है, if we make it react with this metal, then we get this. That's pretty straightforward. So I was hoping to complete at least till elimination, because you questions in organic, again, you've seen during preparation kya hai. Like you get a lot of application based, you'll get like combination. If this first treated with reagent A, then treated with reagent B, it doesn't make sense if you're able to answer only part of it. SO4. Okay, sulfonation. What is the electrophile?
SO3.
SO3H is correct. Sulfonic acid form hoga. This is sulfonic acid. So COH is carboxylic acid. So instead of carbon, since you have sulfur, SO3H is sulfonic acid. Okay, sulfonate iske liye like positive charge is on sulfur.
SO3 plus H2SO4.
Concentrated H2SO4.
Concentrated H2SO4.
Yeah. So यहाँ पे the way we took nitric acid plus H2SO4, same role H2SO4 is going to play, except it's going to act on another molecule of H2SO4. It'll take away the OH, it'll give you SO3H, which will attack the benzene. And Friedel-Crafts reactions. Go to the next page. Do you guys remember Friedel-Crafts reactions? So what are the two reactions? What do we introduce in Friedel-Crafts reactions?
Acylation and alkylation.
Correct. So acylation may, let's look at acylation. So acylation may, what are you introducing?
Acyl.
Acyl group, yes. Structure क्या है acyl group का? Don't remember? Acyl is when you have C double bond O. So this is an acyl group. Yeah, there's a positive charge here. So यहाँ पे usually you start off with acyl halide, which is C double bond O Cl. Acyl halide, again anhydrous AlCl4, AlCl3.
What's the difference between acyl and ketone?
Ketone is you have another R group only attached here. That's a ketone group. But if you have COCl, that's like an acyl group. So your end product, you end up getting a ketone group, ketone. But when it is in this intermediate state, the way we call just R as an alkyl group, right? So this particular species is called an acyl group. So depending on what you attach here, then agar OH hai, to it becomes an acid. If you attach another alkyl chain, becomes a ketone. If I put an NH2 here, it becomes an amide. So that way it will change depending on what you. But this particular group is called an acyl group.
Ma'am, acyl group is RCOH, right?
Then that becomes an aldehyde.
Oh,
It will become COOH.
No, she's asking COH. If I put an H here, it becomes an aldehyde. So this particular species was called an acyl halide. Okay. The next one is alkylation. So alkylation may you introduce R plus will be your this thing, alkyl group, like CH3 plus, C2H5 plus, that way. How do you get a carbocation? So you take haloalkane, alkyl chloride. So you take RCl, treat it with anhydrous AlCl4, AlCl3. AlCl4 gets out. That's how Cl minus is removed, and R remains as R plus. So this, or if you want, you can note it down as two different things.
First one is acylation, second one.
Yeah. So this is Friedel-Crafts acylation, and this is Friedel-Crafts alkylation. Again, it's all there in the names. Acylation में acyl group introduce हो रहा है, alkylation में alkyl group introduce हो रहा है.
Ma'am,
Hmm?
what kind of questions can come based on the electrophilic substitution, nucleophilic substitution?
Organic chemistry may standard 3 types of question. Either you'll be given, like the direct one is you'll be given the reactant, and it'll be mentioned that it is treated with CH3Cl in the presence of anhydrous AlCl3, and you'll be asked what is the product. Or you may be given like when chlorobenzene is treated with a random haloalkane X in the presence of anhydrous AlCl3, then so and so product is formed. Then you'll have to identify X. Or chlorobenzene itself can be a question, a haloarene X or a random compound with molecular formula so and so. When it is treated with this, we're going to end up getting this particular thing that way.
So I have like a silly doubt, but the electrophilic the substitution reactions, that comes under chemical reaction.
I mean, all of these are chemical reactions, but
But different section, chemical properties, physical properties. So all this we're doing is under chemical.
yeah, we are doing chemical properties of haloalkanes and haloarenes. But electrophilic substitution reaction is simply any substitution reaction where electrophile is the one getting substituted is an electrophilic. So that's why even in the preparation of chlorobenzene, electrophile is the one attacking chlorobenzene, right? So we studied it under preparation of chlorobenzene because that's what is our final product. But that's also electrophilic substitution. Yahan pe, because we are talking about what sort of reactions chlorobenzene undergoes, electrophilic substitution is one of those reactions. So we're talking about it under chemical properties. That's what I said. Even for nucleophilic substitution, it's not simply a reaction of haloalkanes. Like any substitution with a nucleophile is nucleophilic substitution. It will apply to alcohols also. It will apply to cyanides also, for that matter, if Cn minus is the one getting substituted. Okay, so don't pigeonhole it into this. Don't be rigid. Just note down the logic because it will be applied in a lot of places in organic, in other chapters under other compounds. Okay. Yeah. So products we discussed would be a mixture of ortho and para. Sometimes ortho may be more, sometimes para may be more, depending on, you know, what are the other factors that we are introducing. But yeah, so that's about it for electrophilic substitution. Like these are the 2 major points you need to know. Then next set of reactions. Okay, I think we made good time. Elimination reactions. Do you guys remember? Have you heard of this before?
Beta elimination
Yeah, where have you heard this?
in hydrocarbons.
Yes,
Alcoholic KOH.
that is the reagent used. But like, what happens during elimination reaction?
Halogen is
Removed from the alpha carbon and hydrogen from the beta.
Yes, removal of a small, elimination of a small molecule. Okay, so if you're doing elimination for alcohols, water is the one being removed, OH and H. Here we're talking about properties of haloalkanes. So the small molecule that is removed will be HCl, HBr, whatever. Okay. Again, important note about elimination reactions. SP again, arenes will not undergo this. Only haloalkanes will undergo this.
Why?
Why? Okay, so we'll discuss the mechanism, then figure out if you can see why. Otherwise, I'll discuss that afterwards. Okay. So only haloalkanes will undergo roughly generalized reaction. If I have CX, others can be whatever. If there is a hydrogen over here, there will be an elimination of a small molecule like HX, and it will result in the formation of a double bond. Always what happens in elimination is, if you start off with sp3, you start off with single bond, you end up with a double bond. If you start off with a double bond, you end up with a triple bond. Eliminate हो रहा है ना, तो ये bonds form करने के लिए और कोई atom नहीं मिल रहा है, so these two carbons form it with each other. Okay. Also this happens like, because you need a small molecule to go, this is called a beta carbon. So you will find that this reaction takes place with haloalkanes with a beta hydrogen. Beta hydrogen is hydrogen on the beta carbon. When you treat it with alcoholic KOH. So this is again quite important. Alcoholic KOH is, you mix KOH in ethyl alcohol or any alcohol. Most common is ethyl alcohol. What do you use? You end up getting an alkene plus HX. So this minus HX talked about. So this hydrogen is always from the beta carbon, and the X is basically yahan pe, whatever X is over here. So you call that an alpha carbon. Okay, so this is the generalized reaction. Important to note down what reagent you're going to use, alcoholic KOH. Important that there needs to be a beta hydrogen. Agar ye nahi hai, to elimination hone ke liye, there is no source. Elimination won't take place. Yeah, and you end up getting an unsaturated. So I already told you guys last year, every single most of the reactions will be very, very, very repetitive. So you already studied this in preparation of alkenes, because that is the one being formed. Now we are studying it as chemical properties of haloalkanes. So principles, reaction, whatever major points are there, everything is the same. So let me know once you guys are done with this, then I'll do the mechanism.
Done.
Okay. Arnav is done. Smera is done. Sanskriti, Smera, Arnav, and Adit, you guys have been really quiet. Like, if there's any part, any question you have, any part that you didn't follow, ask.
Sure, ma'am.
So can I assume that you guys have been following Abhi tak pura?
Yes, I'm just trying to absorb and write it also because we're switching between physical and organic. So that's why.
I know school में वो चल रहा है. But abhi
Ma'am,
focus on this, and then during the weekend or something, then you can like revise and go over it. Okay. Yeah. Kaveri?
HX में you've written beta alpha. What is?
So the hydrogen is from the beta carbon and the halogen is from the alpha carbon. So this particular carbon is called alpha carbon, and uska adjacent is beta, and then uske baad will be gamma, uske baad delta. So you go through all the Greek alphabets like that. Usually this is the convention all of organic chemistry may whatever carbon the functional group is attached to, that is the alpha carbon.
But like, what is carbon in HX? Where is the carbon there?
Where is the carbon? So like this is from the beta carbon. This is the hydrogen. It's not a random hydrogen that comes from somewhere else. This is from the beta carbon. And the X is from the alpha carbon. So agar X yahan pe hai, don't think that hydrogen will be from the same carbon. It is always from the adjacent carbon. That's important to know.
And what was that thing ki if there are more than one beta carbons, how do you decide?
Next step. Finish noting this down. Then I'll do the mechanism and then we'll look at multiple cases. Okay. Rishit, Sanskriti, Arya, Sia, you guys finished yahan tak?
Yeah, I sent it earlier.
Okay. All right. So the mechanism is simple. So alcoholic KOH is basically ethyl alcohol, let's say C2H5OH plus KOH. Usually, agar base, if you take NaOH, KOH, aqueous hai, to you dissolve it in water and that's the reagent you use. But elimination ke liye, you need alcoholic KOH. The reason for this is when you mix both of these, this results in the formation of C2H5 hona chahiye. C2H5O minus, and you have like K plus and H2O. So this is what kickstarts the whole reaction. This is an extremely strong base. Okay. So last year when we did equilibrium, usme we learned the concepts of acids and bases. हर एक acid का conjugate base होता है, हर एक base का conjugate acid होता है. Do you guys remember all these concepts?
Yes, ma'am.
Yes, ma'am. Do you remember the relation between acid and its conjugate base?
If it's a strong acid, then it will be a weak conjugate base. Right?
Correct. Yes. And the
Weak
vice
acid.
versa. Weak acid, strong conjugate base. Would you consider C2H5OH to be acidic in any way? Like, iska acidic properties kitna rahega, kaise rahega?
Maybe basic, yeah.
No, not even basic, kyunki ye ionic nahi hoga na. You need like specialized conditions to make it basic. But definitely not acidic, right? Yeah. So if you consider iska conjugate base, where you remove the H plus and the remaining anion, which is this species, this will end up being a strong base because it wants to take H plus in any way it can. It's an extremely strong base. So that's a very important factor, and that is what is essential for this whole reaction to happen. So when we have alcoholic KOH and we mix it along with our haloalkane, yahan pe there is X, yahan pe let's say there's hydrogen. So the strong base, I'll just call it B minus for simplicity. the strong base is going to attack the hydrogen here. So it wants to accept H plus without the electrons. So this hydrogen is gonna give up its electrons. So that'll be taken up by the carbon. So this carbon is going to be like, okay, too much electrons, too many electrons. And because यहाँ पे already थोड़ा delta positive है, halogen is anyway electronegative, these electrons shift over here. So what essentially tends to happen is you get C double bond C, and this base combining with the H, so you have BH and X minus. So your alcohol initially C2H5OH jo tha, from this you get your C2H5OH back. Essentially, if you look at the reactant and the product, you've lost an H plus and you've lost an X minus. So that's why we say it's elimination of a small molecule like HX. Okay. So follow the electron movement carefully. Strong base wants to take H plus at any cost. So it attacks the hydrogen on the beta carbon. And it is easy for it to attack the beta hydrogen only because beside it, you have an electronegative compound that's ready to take electrons. So these electrons shift over here as these electrons shift over here. Again, that plus I effect, because these electrons are attracted, this carbon, because of its slight positive charge, it extends that induction effect throughout the chain. So it kind of, tries to pull on the electrons towards itself. So it's easy to attack the beta hydrogens most easily. Yeah, Kaveri?
This what you're doing now is like the mechanism.
Yes. This is the mechanism for elimination. This is how it happens. Okay. So yeah, so in this case, X is the leaving group, B is the base, strong base. Okay, so that's how it happens. Now, coming to your question, like what if there are multiple hydrogens on either side? Like suppose we have something like CH3, CH, CH. Suppose we have this compound and we make it treated with alcoholic KOH. तो अभी दो possibilities है. So this is alpha carbon, this is one beta hydrogen, this is the other beta hydrogen. Adjacent है दोनों in relation to this. So possibility, this is one possibility. CH double bond CH CH3, और इधर से भी जा सकता है. तो दोनों में से which one will be the major product? Which will be preferred, or will it be 50-50?
First one.
First one. Okay, why?
More substitute.
More substituted. Okay, so this, how do you decide which product is given by Sedsev rule?
Like the one which has more methyl groups connected to it.
There you go. Yes. So this is the major product and this is the minor product. So this will be major because double bonded carbons may there's like this there's two CH3s attached to the double bonded carbons. In this case, you only have like one alkyl group attached to the double bonded carbon. If you want a revision of Sedsev rule, preferred alkene is the one with more alkyl groups attached.
Ma'am,
Yep.
so in beta elimination, we use alcoholic KOH and the halogen is eliminated. So then why do we use a base, like, to explain the mechanism?
So the base in this case is C2H5O-. I just generalized it by saying B minus because we need a really strong base. You might as well just write C2H5O- here. Same thing.
Why do
So we need a
But why do we need a base?
Yeah, why do we need a base to explain this mechanism?
Because it is the basic. Okay, do you guys remember what is a Bronsted base? Like, what is the definition of a base? How do you define bases? One
Proton acceptor.
proton acceptor. And the whole reason why elimination is taking place is because this proton is getting removed. So unless you have that proton accepting nature, this reaction will not happen. So these are all like the major points of elimination reaction. So I'll keep reaction with metals to the end. So we'll summarize substitution, elimination, probably do some questions.
What is the BH that you've cut out?
Oh, like, so the base takes the hydrogen. So you get BH. So if it was C2H5O minus, combines with H, so you get C2H5OH. So in the mechanism, if you note it down as B as like a generalized base, you can write BH. But if you write it in terms of C2H5O minus, write C2H5OH. Basically, whatever.
So here
use,
we won't get HX, right?
H plus and X.
Like that is
So
the
essentially,
usual one.
yeah, you get K plus here, H plus and OH minus, right? So solution may you end up with H plus, O minus, X minus, K plus. So you can also look at it as basically elimination of H plus and Cl minus. So it's not HCl molecules as a gas that you end up getting as a byproduct. It's the elimination of H plus and Cl minus. That'll be there in the solution.
No, but in the general one for beta elimination last year, they had given HX as the site, as the byproduct.
Yeah.
Yeah,
'Cause
but here we are getting BH and X minus.
That's intermediate, right?
the end of the day, see, we started off with C2H5OH, we got back our C2H5OH. If you look at the solution, we'll have K plus, OH minus, H plus, and X minus. So essentially, if KOH, if we consider KOH also to be regenerated, we'll be left with HX as a molecule that's left as a byproduct. That's why we don't focus so much on balancing when it comes to organic reactions. We focus only on the substrates majorly. Okay. Everybody's done noting down yahan tak? Kaveri, Sanskriti, Smera, Adat, Rishit, Arnav.
Yes, ma'am.
Okay.
Not done.
Done.
Okay. So now we learned about substitution. When it comes to haloalkanes, haloarenes is pretty straightforward. Electrophilic substitution hoga or kuch nahi hoga. But when you have haloalkanes, substitution ho sakta hai, like nucleophilic, in which case it's either Sn1 or Sn2. या फिर elimination हो सकता है. So if you're simply given a haloalkane, जैसे C2H5Cl, and you're given a reagent, treat it with KOH. So how do you figure out क्या होगा Sn1 और Sn2 या फिर elimination हो सकता है क्या? So to figure out what reaction will undergo, like when you're given a question, you need to figure out, you need to predict कि क्या products होगा. First, look at nature of the Rx. Okay. So, like, one is pretty obvious if it's a strong base. Like, अगर alcoholic KOH है, so it's pretty obvious कि elimination ही रहेगा. But if you're not able to figure out कि what is the strength of the base, if you're confused, substitution होगा या elimination होगा, then follow these steps. Like look at the nature of Rx, the alkyl halide. So if it is primary, you can be sure कि it's going to follow Sn2 mechanism. If it is secondary, substitution हो सकता है और elimination हो सकता है. So in this case, you need to check whether, what is your nucleophile. So check on the nucleophile. Then if it is tertiary, again, same thing. It can be substitution क्योंकि उसमें भी beta hydrogen है, or elimination. So check. So in this case, क्योंकि you're looking at a tertiary this thing, check the stability of the carbocation. Okay, next, if you go by strength or size of the nucleophile or the base that's given of the reagent. So if you have a bulky nucleophile, then you end up with elimination reaction. We have a smaller nucleophile, Cn minus, OH minus, like just 1 or 2 atoms long, then you get substitution. Like abhi we saw, like alcoholic KOH hone pe, you have C2H5O minus, which is big, like oxygen ke saath you have a whole alkyl group attached. But if you have OH minus in the solution, so smaller nucleophile prefers substitution. That's the easier reaction to take place. So we'll go that route. And apart from this, you can look at the reaction conditions. Ionic hai, polar hai, non-polar hai, solvent. So all of those, what is the temperature, pressure? So based on that, you can figure it out.
Ma'am, if it's tertiary, wouldn't it prefer Sn1?
Sn1, yes. So here, okay, instead of so if it is undergoing substitution, it's pretty straightforward Sn1. But there's a possibility elimination bhi ho sakta hai. So that's why you also need to consider what nucleophile or base, like what is the reagent you have along with it.
Ma'am, so why is it written check stability of carbocation? Isn't it more stable for tertiary?
Absolutely. But in order to check the final product, like if you're trying to decide simple, if you have a simple tertiary, this thing where it's just this, pretty straightforward, Sn1 hoga, bulky hai nucleophile to elimination hoga. But if it is not as simple as that, suppose you have only 2 and then this is also attached to something else, then you need to check which carbocation is more stable. So even in the case of elimination, kaun sa beta hydrogen, you need to bring in Sidsif rule into picture. So other factors that you need to consider. We'll do some questions so it'll get clarified. So we'll build towards this.
Ma'am, can we take a break?
Okay. Actually, I want to ask you guys one thing. So after this, we're pretty much done with the chapter. We only have some reaction with metals, which is 1, 2, 3, 4, 5 reactions. That's it. And they're all pretty straightforward. Like chlorobenzene, when it reacts with sodium, kya hoga? When it reacts with magnesium, kya hoga? There's no mechanisms and all involved. So either we can finish off the chapter now and then focus on only questions in the offline class, and next week we can start off with a new chapter. Or should we do some questions now and on Saturday, and for the small part, like leave it for next week? How do you guys want to proceed?
I think we should finish it first and then do others.
We can finish it in class, then we can do it today, like the chapter, if it gets over today.
Yes, it'll definitely get over today. We have like 50 minutes, an hour, right? We just have a few more reactions. That's it.
And ma'am, we'll solve it on Thursday and Friday, like in Flipper and all in one.
Yes. Okay, so
Miss, when will you, sorry, for the questions, when will you take class?
Saturday, offline session. Like last week, physics thana, that way this Saturday we'll do chem.
Ma'am, for those who are not joining offline or not
Offline.
attending offline.
I'll send a Zoom link and then yeah, you guys can join in.
Okay.
Also, ma'am, will it be conducted in SV Road? Like sir told, right, he rented a place in SV Road. Will that also be used?
No, because Rishit, honestly speaking, you'll be the only one who'll be attending there. So it'll be in Malad Center only. I think.
But has it not been rented? That is why.
It's rented. Abhi grade 10 classes happening on Saturdays. So.
I think 3 to 4 people will come, right? I mean, Kaveri also stays in Bandra only, I think.
Because
We've checked it. Like that's why like sir also must have asked you guys preferences, no? The online, offline. Not there.
And is it not possible in a school building, like the Khar one or the OJS campus?
We'll figure it out. We have a whole week for it, Rishit. We'll see. So are you guys willing to come? Arya, Sia, Kaveri? So based on that, we can decide timings and all that. Isliye.
if it's at Bandra, yeah, I can try.
Yeah, Malad I can't come.
No, Bandra,
Yeah.
I'm asking. Okay.
It's far for me either way, so.
Where do you stay, Sia?
Andheri East.
Andheri East. Okay. Okay. So if you guys are willing to travel, then we can consider car definitely. All depends on you guys only.
So like the car building was not available or what? So sir decided to do it on SV load or something is happening on the car building.
Yeah, and then your board exams are also starting, right? So building will not be available. Yeah.
I am willing to come for the SV road. It is very near. I don't know where in SV road, but SV road itself is very near to my house.
So
Yeah.
it's very close to your school building. It's like 600, half a kilometer from your school building on SV Road. So by when will you guys be able to let me know for sure? So based on that, we can decide.
I can 100% come. I can actually just walk to my school, so it should not be that far also
Yeah.
from there.
Yeah. Same.
Arya also, okay. Kaveri, what about?
Yeah.
So I have another class at the same time, but if I can come for a few days and see how, if it's like really helping me, then I can come. If it's in, obviously if it's in near SV, I can't come to that.
Okay. Okay. So we'll see, we'll figure it out. We'll figure like different timings रखना है because Malad also these guys are coming to the center, right? We'll plan. अगर कोई changes है, अगर कुछ हो रहा है तो we'll let you guys know. We'll put it on the group. Okay. Okay. Now coming back to this. So one last reaction that haloalkanes, haloarenes undergo is reaction with metals. Okay. So reaction, whenever these react, like the haloalkanes, haloarenes undergo reaction with metals, we'll go one by one. The first one, reaction with magnesium. Does this sound familiar to you guys? So haloalkanes Rx, when it reacts with magnesium in dry ether, because we don't want to ionize, like we don't want magnesium hydroxide and all, what do you get?
RMgX.
Yes. What is this called?
Grignard reagent.
Correct. So Grignard reagent, get very familiar with it because this part of Grignard reagent can break easily. And this is the only way you get like carbanion, because magnesium is electropositive. So whenever you treat it with even the mildest of mild acids, something like alcohol also, you end up getting alkanes, because R reacts, like joins up with H plus and gives you alkanes. Okay. So even though, okay, some important points about Grignard reagent, the CMG bond is covalent, but again, magnesium being highly electropositive is highly polar. And that makes this particular compound extremely reactive. So you never use Grignard, like you don't find bottles of Grignard reagent. You always have to prepare it freshly for whatever reaction you need. Okay. So it is so polar that it's basically ionic only. So whatever slight trigger you provide, it's going to split into R minus and Mg plus. So that makes it extremely reactive. To give hydrocarbons. So you get hydrocarbons with any source of proton. So when we talk about source of proton, so even things like alcohols, so these you won't consider as acidic. Amines in fact are known for their basic nature. The way you have carboxylic acids as organic acidic compounds, amines are supposed to be. Amines are basically RNH2. They're very similar to ammonia in how they behave, but in the presence of RMgX, because magnesium is highly electropositive, this also ends up getting acidic nature. Like it pulls the hydrogen from this and forms hydrocarbon. Water is supposed to be neutral. That's what we consider water to be. But in the presence of RMgX, this also gets acidic nature. Pulls the H plus from water to give hydrocarbons. So even these are sufficiently acidic. And when we say acidic, I don't mean like your normal definition of acidic as a source of proton. Like this is, the compound is capable of pulling H plus even out of compounds like these, that we consider it as an acidic compound in this particular situation because they're all losing an H plus. Okay, does that make sense? So, for example, if I have CH3Cl, make it react with magnesium in dry ether. you get CH3 MgCl. And this, even if I treat it with C2H5OH, alcohol is not acidic, but this compound is strong enough to pull the H from this. So this basically attacks the H plus, gives me methane plus Mg C2H5O Cl. Okay, yes, done.
No.
Okay.
I'm just
Is it C2H3O or C2H2O?
What did we take here, Rishit?
C2H5OH.
So यहाँ पे if this pulls out the H plus, what will be remaining? What will you end up with here?
Sorry, could you repeat?
So if the Grignard reagent pulls H plus, so what other ion will remain here?
C2H5O.
So that's what this. That's what attaches itself here. That's what I'm saying. Don't blindly copy. Like try to follow ki reaction में क्या हो रहा है, what is going where. Okay. 3 people have finished. Smera, Kaveri, and so if you let me know when you're done.
done.
And it's done. Rishit is done. Arnav, Arya, Sia.
On my side done.
Okay. Next one is reaction with sodium. Under sodium, we have like 3 reactions. Okay, before we get to sodium, even haloarenes are capable of forming Grignard reagent. Okay. So suppose we have bromobenzene plus magnesium in dry ether. You get this. Same application, if you want to prepare benzene, treat it with a proton. And if you want to add a benzene ring to another compound also, like add it, like prepare a carbocation and then treat it with Grignard, like this particular Grignard's reagent, you end up adding a benzene ring to that compound. Same mechanics, same specifics, all of that. The next set of reactions, sodium, we have 3 reactions of haloalkanes with sodium. You guys have studied this again during preparation of alkanes. The first one is Wood's reaction. Do you guys remember?
Soda lime.
Only sodium, right?
Yeah. Soda lime, yes, you heat haloalkanes with soda lime, you get alkanes. That's a method of preparation of alkanes. But Wood's reaction is when you heat this with only sodium. So Rx plus Na in dry ether again. So what happens in Wood's reaction? Do you know what is the speciality of this?
You get even number of carbons in the
Yes.
product.
Yeah. So 2 moles. So you get RR plus 2 NaX. So the sodium pulls out the halogens and whatever is remaining joins with itself to get double the whatever haloalkane you took this thing. And the same reaction, if you end up doing with benzene, that's called Fittig reaction. The only difference between Wood's reaction, Fittig reaction is that one is with aliphatic haloalkanes, one is with haloarenes. And dry ether. So these two end up joining. So this is called diphenyl. Phenyl groups, 2 of them attached to each other, so diphenyl. That's 2NX. And the third one is called Wood's Fittig reaction. Can any of you guess what that entails?
For both.
Both.
Yeah. So you take a haloalkane and a haloarene, they basically attach with each other, and that's Wood's Fittig reaction. So Wood's Fittig reaction is you have a haloarene and a haloalkane. Rest of it all remains the same. Sodium in dry ether. So instead of doubling up, the arene, the alkyl chain gets attached to the benzene ring, gives an X. Then we did magnesium, we did sodium. Next, reaction with lithium. So reaction with lithium, very similar to that of magnesium, diagonal relationship and all that. So you get an organometallic compound similar to Grignard reagent. So suppose I take Br, lithium in dry ether, you get this. And finally, similar to Fittig reaction, if you heat iodide with copper powder, this is another method of preparation for diphenyl. Yes. CU. Heat. Then you end up getting diphenyl and copper iodide, similar to the reaction we have with sodium. So that's all we have with reaction with the different metals.
After metals, what is that?
That's it. I think we have one more reduction reaction. So if you reduce haloarenes, what do you end up getting? Reduction matlab addition of hydrogen. So क्या आएगा? So halogen के place में you have hydrogen added to it. So you end up
Does
getting
this copper powder is that Gatterman something like that?
no, Gatterman coke is different. So that's when you're preparing a haloarene. So this is called Ullmann's reaction. Ullman. So Gatterman reaction, yeah, good point. You remember that. So in that case, you don't heat a haloarene. You heat the diazonium salt with copper. In that case, you don't heat it with copper also. You heat it with a copper halide, copper chloride. So then that
Which one?
Gatterman reaction.
Oh, okay.
Yeah, so that's used in the preparation of haloarene. Here, if you're directly heating haloarene with copper powder, that's Ullmann reaction.
Why is everything with dry ether?
So if you don't use dry ether, okay, what is difference between dry ether and common solvent like water or alcohol and all that?
Polar solvent, non-polar solvent.
Exactly. So since you're doing the reactions with metals, if you use any polar solvent, if you use water, then sodium will not stay as sodium anymore. It's going to turn into a sodium ion, and then you're going to have OH minus ions, H plus ions in the mix, and you're not going to get the reaction that you want. So if you want the reaction to take place between the organic compound and the metal, you need a solvent that won't interfere with either of these. So that's why you use dry ether in all of these.
What have you written beside copper? Besides copper powder?
Ullmann reaction. Ullman. That's the name of this reaction. Ull.
Yes, but why dry ether? Why not acetone?
Acetone also, like acetone has a C double bond O, right? So there is some amount of polarity here, which you won't find in dry ether.
Okay.
So ether ka this thing is, it's surrounded by alkyl groups on both sides. So whatever polarity you end up having gets cancelled out on both sides. So ethers are in fact one of the most inert organic compounds compared to others. Okay, that's it. So these you can remember them, no problem, but focus on substitution reactions, unke mechanisms and all, because they will apply to other compounds as well. You know, whatever principles you learn there. Substitution is one, elimination is one. So these two, learn the mechanisms, figure it out, like try and know them inside out, because yeah, they are the most important parts of this chapter. Nice, we're done fairly early. Okay, so we'll do like MCQs, simple ones, one step ones, but it's going to strengthen your concepts. After that, you can look at the, you can practice from Flipper, you can do the topic practice from there. Okay. So you guys ready? Want to look at it?
Yes.
Okay. Yeah. Fifth one, which will undergo Sn1 reaction most easily?
D.
Was that B or D?
D.
D. Okay. Arya says D. Rest of you, give your answers. Okay, Sia also has sent her answer. Kaveri, Sanskriti, Smira. Guys, Adit, Prishit, Arnav. Okay, 3 people. Smira has given the answer. Kaveri also has given. Arnav, Prishit, okay. Adit, yes. Nice. Kaveri gave the reason also. Very good. Sanskriti. Yeah, Sanskriti, you're the only one who's remaining. What is the answer? Sanskriti, are you there? Cool. All of you, yes. Arya also has given the answer. Very nice. So D is right. Iodine, I is the easiest leaving group because bigger size. This bond will be easiest to break out of these 4. That will be the most ready reaction. So either Sn1 or Sn2, I is the best leaving group. That'll be the fastest. Next, which of the following compounds will give Rasomic mixture on nucleophilic substitution by OH minus? So basically nucleophilic substitution ho raha hai. In which case are you going to get a Rasomic mixture? So you're given 3 of them. Which one will it be? So when you send, are you going to like send the option number? Okay, don't send a wala number. Just send A, B, C, or D.
Ma'am, could you show the question once again?
Question is asking, so all of these are undergoing nucleophilic substitution, which will give Rasomic mixture. Arya, is that like send the option number A, B, C or D? No, यहाँ पे options है.
Oh, okay. Sorry, I didn't see the one.
हाँ. Okay, Rishit, Arya and Sia have answered. Okay. Kaveri, same thing, like there are options here. A, B, C, D. So they're indirectly asking you in which case are you going to find Sn1 mechanism happening. Another thing that you guys need to remember is it's asking about a Rasomic mixture. So you need 50% D and 50% L. तो अगर कोई symmetrical carbon है, मतलब you don't have question of chirality at all. So that's another thing you need to consider.
If it's symmetric, like if it's already racemic, then it can be Sn2 also. So we'll still get a racemic mixture only, right?
How do you know it's already racemic?
It's not mentioned. We'll give Rasomic mixture on nucleophilic substitution. So Smera, Rishit, Arnav, Sanskriti have not answered yet.
I have.
You have? Oh yeah, you sent your answer. Yes, saw it.
Ma'am, I don't know the proper reasoning, so I'm not able to.
Okay. Okay. There've been a mixture of answers. Couple of people have sent A, and lots of people have sent C. So let's take this one by one. Okay. So Rasomization ke liye, like since it specifically asked about Rasomic mixture, one, Sn1 mechanism chahiye. Two, we need an asymmetrical carbon. So first look at chiral centers in this. Option 1, if you look at it, यहाँ पे C है. If Br gets replaced by OH, I have CH3H ethyl group OH, तो इसमें है chiral center. यहाँ पे will this give me optically active isomers?
No, it's not chiral.
As
There
a
are two.
CH3 है, यहाँ पे CH3 है. So this is not going to be giving me, this is not going to give me any Rasomic mixture at all. Remember, definition of Rasomic mixture is 50% D plus 50% L. So DL का question होना चाहिए. There should be D and L isomers here. So if you don't have any DL isomers, यहाँ पे कोई chiral centers नहीं है, so this is not going to be a Rasomic mixture. It's going to be like whatever final this thing that you get. Okay. So this will automatically eliminate B and C because we don't have to. Now either one or both 1 and 3. So यहाँ पे do we have a question of chiral carbon centers? Since I discussed this compound, when you guys tell me.
Yeah, it can be chiral.
Where is the chiral centers? Yeah.
The second carbon, like it has 4 different functional groups attached.
Yes, but when this undergoes nucleophilic substitution, will it go Sn1 or Sn2 mechanism? Again, there's a tertiary carbon here, no? Remember what I said, like if there is a chance for stability, it will go ahead. Like this is going to rearrange itself to have CH3 over here, CH3 over here, and get that carbocation here. So after substitution, you're going to get the OH over here.
Could you repeat this, ma'am?
So in
Yes,
this,
yes, please.
yeah, this is the rearrangement case that I discussed earlier. So bromine is over here, but यहाँ पे we have a tertiary carbon, right? So rather than SN1 with like SN1 के लिए ये पूरा bulky group है इधर. Secondly, because there's a tertiary carbon, this will rearrange itself like ये वाला hydrogen in that hyperconjugation वाला effect. This is going to rearrange itself as C2H5 and CH3. Because tertiary carbocation is more stable, once it loses bromine, hyperconjugation happens and this hydrogen will migrate over here to give you a tertiary carbocation. So once that happens, step 2 mein, your final product is going to look like this.
Ma'am,
Okay.
I'm still confused how the third one is not chiral.
Look at the final product here. For that, you need to understand how did we get the final product? Did you get this? Waiting, yes, no.
Could you repeat?
Did you understand how you got this?
No.
Okay. So you may think कि primary carbon है SN1 mechanism होगा, but adjacent I have a tertiary carbon here.
Yes.
तो tertiary carbon है मतलब whenever the scope, like whenever you have a tertiary carbon, either like if the halogen is on tertiary carbon or if it is adjacent to the tertiary carbon, tertiary carbocation is always more stable. So अगर इधर है carbocation, then the positive charge will migrate here. Like hyperconjugation effect say, this hydrogen will move over here and you end up with a tertiary carbocation. Like rearrangement takes place. We discussed this earlier.
Yeah.
It was the exact case I have taken. So once I get a tertiary carbocation, substitution ke baad the OH minus attaches itself to this carbon.
Yeah.
So now tell me, is this chiral or achiral?
Achiral. Correct.
Yeah. So
So basically, instead, we would assume that because the Br is there, the OH would be there, but that's not the case because the OH will attach itself to the central one.
Yes. So like agar tertiary carbon hai, matlab the compound will prefer forming a tertiary carbocation.
But like, how do we know if it rearranges or not?
Kyunki Br is adjacent to the tertiary carbon. If you see a possibility, it will happen. If it is somewhere far off in the compound, it won't. But it's like right here. Agar yahan pe positive charge hai, it will be more stable here. Just like
Ma'am, can't
Miss, how do we decide which carbon would be the chiral center?
so like that's what you figure out the mechanism. तो end product में Rasomic mixture चाहिए मतलब chiral center होना चाहिए. Then you look at the end product and then see chiral center यहाँ पे है कि नहीं.
Ma'am, can't we just consider the carbon to which bromine is attached? I mean, that itself is not chiral. So can't we say that
So
it
it is
won't
not
happen?
the reactant is not chiral, but the question says कि nucleophilic substitution के बाद which gives the Rasomic mixture, right?
Yeah, so if bromine is substituted, like before the rearranging also, it's not chiral, right? That carbon.
But
Because there are two hydrogen.
But that's not what is happening in reality, no? Like that's the whole point of learning about mechanisms key, because there is a stable alternative, it is going to rearrange and go towards that stable alternative.
How before rearranging it's achiral?
Okay, I'm
It's
gonna
chiral, not achiral.
Okay, now do you observe?
I mean, yeah, it's achiral. Yeah, because there are two hydrogen.
No, this carbon is achiral, but this one is chiral. No? You have C3, you have
Yeah,
C3.
that one is chiral.
Yeah.
So you said we see the reactants and we see that it's not chiral, so that's why we can conclude that the product will be the same way.
Who said that?
No, like it was Sia's doubt, right? She said that before.
No, she was asking why can't like substitution ke baad matlab like why can't we just put OH over here and then figure out that this is either way, like even if you substitute it over here, iska koi like there's no difference in this particular carbon, so not gonna make much of a difference that way. Okay.
So like, can we find out without rearranging?
You can, but it won't be 100% accurate. Like because the question is asking about the final product, just be safe and figure out the final product and then figure out the chirality.
Okay.
It won't be foolproof, is what I'm saying. Yeah. Which one is asymmetric? This I want you guys to answer in like 30 seconds. Fadafat. Isme you only need to look at this carbon atom and see in which case is it asymmetric. Yeah, Sia answered. Sia, check your answer again. Just because I said 30 seconds, don't overlook things.
Asymmetrical, right? Not symmetrical.
Kaveri, check again. Arya Smera, well done. Yeah, that's why, like, don't be in a hurry. Like, be a little careful. 30 seconds is a long time. Arnav and Adit, correct? Kaveri, check your answer. Rishit, Sanskriti, and Arya. Three of you guys, I'm waiting. Rishit, good. Well done. Arya, are you there? Kaveri,
Yes, yes.
Arya already answered. Okay, I'm sorry. Arya answered. Sanskriti looks like Sanskriti is disconnected. I have to check with her. Kaveri, what did you answer? Okay. How do you figure out like which one is asymmetric?
All four different.
Huh. So option 1 may all 4 are same or different? Like the first compound, not option 1. HIBRCl. चारों अलग है ना? So this is asymmetric. Option 2, DIBRCl. All 4 different. Option 3, HOH methyl ethyl. Again, all 4 different. And option 4, we already have H and H. So this is not asymmetrical. So 1, 2, 3, B would be the correct answer. Yeah. 8 is also the same thing. Yeah. So rest of the questions we'll do on Saturday, when like we'll focus only on questions on Saturday. If you want Friday I'll give you guys like a list of things that you need to revise. So you can go over it and